Morning, everyone. We are from Group 9, and our teammates are Sashank, Venkat Tarun, and myself, Chandana. And my group project topic was extending MySQL with modern catching strategies, a comparative analysis of LIRS, TinyFLU, and S3-FIFO for query performance optimization. And today we are here to explain our presentation. The, the main introduction of this is the MySQL 8.0 removed its native query cache due to performance and concurrency issues, creating a gap in handling repeated query workloads. Our project addresses this by integrating a pluggable caching framework directly into MySQL's query pipeline. We introduced three modern caching strategies, which is LIRS, TinyFLU, and S3-FIFO, each designed to improve cache efficiency across different workload types. This system integrates query fingerprints, catches for cached results, and decides whether to reuse or compute the result. Our approach enhances performance for read heavy applications like dashboards and analytics while preserving ACID compliance and MySQL's core behavior. The main motivation of this is the The modern applications often execute the same query repeatedly, especially in dashboards and APIs. The many more modern applications, such as dashboards and APIs, frequently execute the same queries without query level caching. MySQL processes each request from scratch, wasting resources and increasing response times. Although InnoDB buffers data pages, it cannot avoid the overhead of parsing and executing repeated queries. Developers often resort to external caching layers, which add complexity and risk data inconsistency. Our motivation is to bring caching back inside the database engine using smarter strategies. By doing so, we reduce redundancy, improve efficiency, and provide a seamless solution for query reuse in read heavy environments. The main problem with native query caching is MySQL's original query cache was removed in version 8.0 due to its inefficiency in high occurrency environments. It's invalidated all related cache queries whenever a table was updated, leading to frequent and unnecessary cache purges. This global invalidation, combined with looking overhead, caused performance degradation instead of improvement. As a result, the feature was disabled by default and eventually decrypted. Its rigid design lacked adaptability and fine-grained control, making it unsuitable for dynamic workloads. Our project reintroduces query level caching with modern strategies that overcome these limitations and support concurrent read heavy systems more effectively. The, the main objectives here are the first objective of this project is to design a modular caching system that can be easily integrated into MySQL. The framework must support multiple strategies including LIRS, TinyFLU, and S3-FIFO, each with unique caching logic. It is positioned between a query phrasing and execution, enabling interception and reuse of repeated query results. This intelligence must maintain MySQL's ACID guarantees and support concurrency without affecting the storage engine. By decoupling the cache logic from the core database internals, we allow establishability and independent evaluation of advanced cache management techniques. And in addition to system design, our objectives include implementing the three caching strategies as independent, interchangeable modules. We develop a benchmarking suite using TCPH for analytical and chase bench for transactional workloads to evaluate performance. Metrics such as cache hit rate, execution time, and memory usage were tracked. The framework also ensures thread safety in multi user environments, avoiding race conditions and lock contention. Finally, the architecture is designed to be generable, allowing future adoptions for other relational databases or newer MySQL versions without major code based disruption. The related work here is LIRS improves upon traditional LRU catching by tracking reuse distance, which better identifies frequently accessed queries. It uses a stack to maintain recent accesses and separates entries into low and high referencing sets. Through effective in file systems and memory caches, LIRS hasn't been widely applied to query result caching. TinyFLU, on the other hand, focuses on intelligent cache admission using probabilistic frequency tracking via count min sketch and a Bloom filter. It is used in systems like caffeine but has not been integrated into SQL engines. Our work brings both techniques into MySQL's native query processing pipeline. And here is the S3-FIFO improves a traditional FIFO by introducing these queues short, mid, and long term to stage queries based on access frequency. This method has shown success in web caching and flash storage systems but hasn't been used in relational databases. Prior MySQL caching efforts relied on static or external application layer caches which lacked adaptability and required complex coherence logic. Research by Gramron and Nordin explored dynamic app side caching but couldn't leverage internal database metadata. Our system is the first to embed S3-FIFO and other adaptive strategies directly to MySQL, ensuring transactional consistency and internal visibility for smarter cache management. The proposed Our proposed framework introduces catching directly into MySQL's query processing path between phrasing and execution. The first step is to normalize queries by removing synthetic differences such as white space, case, and constant values. To create consistent fingerprints, these fingerprints are then hashed and used as unique keys for cache lookup. If a cached result exits, it is returned immediately by passing execution. If not, the query is executed and its result may be sorted based on the caching policy. This mechanism enables efficient reuse or repeated query results and forms the foundation of all caching strategies implemented. Here is the proposed work. To support a flexibility, we design a pluggable architecture where each cache strategy LIRS, TinyLFU, and S3-FIFO implements a shared interference with operations like lookup, admit, and evict. LIRS uses reuse distance to manage promotion and demotion of cached queries. TinyLFU uses frequency estimation to admit only high value queries. S3 FIFO stages entries in three queues, promoting them based on repeated access. Each module can be independently configured and turned for specific workloads. This modularity ensures that future strategies or hybrid models can be added without rewriting the core cache framework. And my teammate Tarun is going to continue from here.
Hello everyone, my name is Venkat Taran. Now I'm going to be explaining about the system design. So in our system, every SQL query begins its life cycle at the parsing stage. The query parser first checks for the syntax correctness and then validates it semantically against the database schema. After validation, what it does is the query is normalized into a canonical form to eliminate the irrelevant syntactical differences. This normalized form is used to generate a consistent fingerprint via hashing. By doing this early in the pipeline, we ensure that logical equivalent queries, regardless of formatting or parameter values, can be identified, matched in the cache. This process is critical to maximizing cache hits and reducing redundant execution. Next slide. In our system, every SQL query begins its life cycle at parsing stage. The query parser first checks for the syntax correctness and then validates it semantically against the database schema. After validation, the query is normalized into a canonical form to eliminate. After parsing and optimization, the query reaches the execution engine, which performs the actual data retrieval and processing. Our cache layer is integrated just before result delivery, allowing the engine to check for a cached result based on the query fingerprint. If a result is found, it bypasses the execution, otherwise the query proceeds normally. This integration is carefully designed to preserve MySQL's ACID guarantees, including the transaction isolation and durability. The execution engine continues to work seamlessly with the transaction manager and lock manager, ensuring concurrency control and correctness. Next slide. So this is the caching layer and storage. The caching layer is positioned between the query execution and result delivery. It uses normalized query fingerprints to perform lookups before execution begins. If no cached result exists, the query is executed and result is evaluated for admission based on the active strategy. This design avoids interference with the InnoDB buffer pool, which handles low-level data usage caching. Our cache operates at the logical result level, enabling reuse of entire query outputs. Together, these two layers, the InnoDB for data pages and our cache for the query results, create a multi-layering cache structure that improves performance without duplicating responsibilities. So next slide, this is the algorithm and observation for the LIRS. So LIRS is a caching strategy that tracks how recently and frequently a query is reused. It classifies cached entries into two sets: the LIR, the frequently reused, and HIR, infrequently reused. So a recency stack helps determine when to promote or demote queries between these two sets. So queries with a shorter reuse distance are prioritized for retention. Unlike traditional LRU, which may evict valuable entries due to temporary inactivity, LIRS adapts more intelligently to access patterns. This makes it especially effective for analytical workloads where certain queries are reissued periodically, but with a high computational cost. Next slide. So this is the tiny LFU algorithm observation. So the tiny LFU is a frequency aware catching strategy that focuses on smart admission rather than just eviction. So it just estimates how often a query has been accessed using a count min sketch, a compact probabilistic data structure, a doorkeeper bloom filter prevents one-time queries from polluting the cache. Only queries with sufficiently high estimated frequency are admitted. Once admitted, entries can be managed using traditional policies like LFU. Uh, this filtering mechanism ensures that the cache space is reversed for queries with high reuse potential. So making TinyLFU especially effective in mixed workloads with bursty or long tail access patterns. So this is the S3-FIFO algorithm and observation. So in S3-FIFO algorithm, it is generally a lightweight catching strategy that avoids complexity by using three FIFO queries. First one is a short term Q1, next one is the midterm, and the long term Q3. So newly admitted queries enter Q1 and are promoted to Q2 and Q3 upon repeated access. This staged promotion ensures that only frequently reused queries reach the most persistent storage tier. So the evictions start from Q1, preserving long-term valuable entries in Q3. S3 FIFO requires minimal metadata and is lock-free, which is making it ideal for high concurrency environment. Its simple structure adapts well to dynamic workloads while maintaining low overhead and strong cache hygiene. The next one is the experiment one, which I'm going to be explaining about, which is called the query normalization validation. This experiment evaluated the effectiveness of the query normalization module over 150, like 150 syntactical differently, but logically, this is equivalent queries were tested to verify it. If they have mapped to the same fingerprint, the normalization process, which involves lower casing, removing white space, standardizing constants, reordering commutative expressions, and all these results showed that 98% of logically equivalent queries generated identical fingerprints while distinct queries produced unique ones. This confirmed that the fingerprint process effectively has maximized the cache hit potential. A few cases like India versus in versus joint rewriting were flagged for future improvement. But overall, the module proved highly accurate and efficient for cache key generation. So here is the next experiment two, which is called the cache integration with the execution engine. This experiment verified whether the cache framework could be safely and effectively integrated into MySQL execution pipeline. The system intercepted queries after optimization and before execution to perform the fingerprint cache lookups. So these results confirmed that the caching layer enhanced performance without disrupting MySQL's concurrency and ACID guarantees. Next slide. And the next slide, experiment 3, will be continued by my teammate Shashank Sribhasham.
So I'm going to talk about the experiment 3, which is the LIRS strategy evaluation. This experiment tested the LIRS caching strategy under a simulated analytical workload with repeated query patterns, and a mix of 50 frequently repeated queries and 150 one-time queries were used to simulate real-world access patterns. And LIRS maintained an 86% of cache hit rate in the medium cache configuration, outperforming FIFO and LRU baselines. Its ability to promote high reuse queries and evict low utility ones was confirmed through promotion, demotion, and eviction patterns. These, even under memory pressure, uh, preserved performance by adapting its LIR or HIR sets effectively, and the results validated LIRs as a strong fit for read-heavy and temporarily local workloads. This is the code like we have used, uh, basically the LIRS simulation, where the user selects the LIRS strategy and enters the SQL queries and observes the cache behavior in real time. Initially, we have the select star from users, where the query results in a cache miss is executed normally. And on the subsequent execution, we have the same query which produces a cache hit, demonstrating the correct reuse. Benchmarking reveals query evictions, transaction handling, and improved latency. And this final ones show that we had two cache hits, seven misses, and five active cached entries. And it confirms that the caching layer correctly identifies the reusable queries and manages its LIRS eviction logic. Coming to the next experiment, which is the TinyLFU strategy evaluation. The TinyLFU was evaluated using a Zipfian workload to simulate real-world query frequency skew. Queries were categorized into high frequency, medium frequency, and low frequency groups, and TinyLFU admitted over 90% of the high frequency queries while filtering out 72% of the low frequency ones and significantly reducing the cache pollution. Compared to the LRU only baseline, the TinyLFU improved overall hits by around 15 to 20%, and the count minimum sketch and the doorkeeper bloom filter used for frequency estimation consume less than 2% of the total cache memory. And this experiment confirmed that the TinyLFU is highly effective at prioritizing valuable queries in mixed workloads, and especially where many queries occur once infrequently. So this simulation demonstrates the TinyLFU caching strategy integrated into the pipeline, and after setting the cache strategy in TinyLFU, several SQL queries were processed. The query select name from users where age is greater than 20 uh, shows a cache miss as it is observed on the first axis, followed by a cache admission check. The TinyLFU admits the query based on its estimated frequency using a count, minimum sketch, and doorkeeper filter. And these cache statistics reveal two cached entries but zero cached hits, indicating a low frequency query did not pass through the filter. And it confirms that the tiny LFU strength is avoiding the cache pollution from infrequent or one-time queries. Coming to the final experiment, S3-FIFO strategy evaluation. And this was tested under a bursty and very stable and hybrid workloads to evaluate its adaptive caching behavior. The one-time users were mostly evicted from the short-term queue, which is the Q1, and the frequently accessed queries were promoted through Q2, which is and the Q3, which are the medium and the long-term queries respectively. In the stability phase, repeated queries achieved over like 85% hit rates. And during hybrid phases, the queue structure effectively absorbed burst traffic without affecting long-term cache quality. And compared to the traditional FIFO, the S3 FIFO reduced the execution time variability by 28% and required minimal synchronization due to its lock-free design. These results demonstrated its suitability for dynamic and high concurrency environments. So in this simulation, we see the caching strategy selected and tested within the MySQL engine. MySQL queries like the select star from orders where amount greater than 1,000 was updated and the order set status were equal to shipped, where ID equal to 3 were processed. Initially, both the queries result in cache miss, but when executed and admitted into the cache, the subsequent invocations promoted them across the FIFO queue segments based on reuse, and the final statistic shows us we have two cached queries, two misses, and zero hits, indicating initially stage population of the cache. And this design of S3-FIFO allows us to have a dynamic promotion and demotion across queues and preparing the adaptive reuse over time. We have a demo video of the implementation of all these three caching techniques. And uh, so we first begin with LIRS, and we have this database management system simulation menu from where we select a choice. And once we select the choice, we give which query we'd like to give, either select, update, or delete. So initially we have given select, and then we can see the cache miss, lock acquired, and transaction started and committed calls over here. And next we go for the second option, which is the update. And here also we see how the cache has been meshed, locked, and the transaction has begun. And then we move on to TinyLFU. And here also we select one of the options from the menu, and we get the benchmark time which has been completed in, which is around 1.32 seconds. And the same one has been done for S3 before as well. Coming to the results, the cache hit ratio is a key indicator of how effectively the caching strategy has been prevented and redundant query execution. The LIRS achieved the highest hit ratio around 85%, uh, and the particularly excelling in analytical workloads with strong temporal locality. TinyLFU also delivered high hit rates by preventing low frequency queries from entering the cache, and S3-FIFO maintained competitive hit ratios across varied workloads by promoting frequency accessed queries through its queue stages. And overall, these three strategies performed better than MySQL's default InnoDB buffer pool over 20%, and these improvements confirm the benefits of introducing query level caching tailored to access patterns and reuse behavior. Our framework basically and significantly reduced query execution time under repeated workloads with caching enabled, and warm cache conditions results in an average around 25 to 30% reduction in total query latency, and the TinyLFU and S3-FIFO introduce minimal memory overhead while maintaining high performance. And the TinyLFU's count minimum sketch and Bloom filter used under 2% of the total cache memory, and LIRS handled constrained memory scenarios gracefully, maintaining strong hit rates. And we can see the benchmark execution time by caching strategy. Uh, Basically, TinyLFU versus time graph, and not just TinyLFU, but also LIRS and S3-FIFO. And this overall improve the efficiency without compromising memory usage or introducing measurable delays in query execution. Each of the caching strategy showed distinct strengths around different workloads, and the LIRS excelled in heavy analytical workloads due to its reuse distance tracking and maintaining stable performance. TinyLFU adapted well to the mixed workloads by filtering out infrequent frequencies and focusing on high reuse entries, and S3-FIFO performed the best in dynamic and concurrent environments. And the modular framework allowed switching strategies without modifying the MySQL code. These results highlight the value of workload-aware caching and demonstrate that no single policy is optimal for all scenarios, reinforcing the need for flexible and pluggable cache design. Coming to the conclusion, by integrating LIRS, TinyLFU, and S3-FIFO directly into this execution path through like the terminal, we successfully reintroduced the query level caching in MySQL, and we have achieved significant improvements and performances in the cache hit rates and memory efficiency. And each strategy demonstrated strengths in different workload contexts and proving value to the adaptive caching. The overall preserved MySQL transactional agents guarantee that required minimal changes to the core engine, and the overall results confirm that intelligent workload-aware caching is both feasible and highly beneficial in model SQL environments and in applications that experience repeated and predictable query patterns. In future work, we plan on extend this framework to supporting hybrid caching strategies that combine all these three strategies. And we aim to incorporate machine learning techniques for dynamic strategy selection and adaptive threshold tuning based on real-time workload. And additional features like disk-based spillover caching and multi-tier architectures are in consideration, and porting the system to other open source databases like PostgreSQL will help evaluate the generalizability. And we also plan to benchmark the system in cloud native environments and real world applications, which enable broader adoption of intelligent caching with within the enterprise grade relational database systems. These are the bunch of references we have used for this project, and thank you.